Okay. So what we're looking at here to start with are some linear equations. Okay? This is from the very beginning of the semester, from before that, in 308, if you had a 308 class. So we're going to start with this to get warmed up. We're going to take these same skills and then apply them to inequalities. So just some general solving of linear equations. You can have at that. Feel free to work together. Call me over as you need help. If there's any places you don't have comfort level with these, we need to make note of that and get that practice and get those questions answered. I'm going to add a couple more up here. Remember that we're following our general strategy, which is kill decimals and percents first, and then get rid of any parentheses and combine like terms, and finally use your addition and multiplication properties of equality to move all the x's to one side and the numbers to the other side, so you solve for x. All of those will awkward there. That's a 5x minus 4 on top. You see that. Okay, so go for it. Where help is needed, feel free to help each other. I'll start slowly working these up here for you to check yourself. Put all your answers in set notation. Decimals or fractions first. Okay. Okay. No fractions or decimals to kill, no parentheses to distribute and combine like terms. We just go ahead and start using the addition property. Here I used it twice in one step. As I start to do shortcuts, remember, if you're not sure I got from one step to the next, ask me. Here I just used the addition property twice in one step to get the 3x over, the net minus 3x over on the left, and that plus 4 over to the right. These are all linear equations, so you're expecting one solution. There's no factoring necessary, no factoring involved, or other quadratic methods that we use just if we have squares.
What's the rest of the
Oh, 3x minus 5.
Okay.
Remember, if you have to kill parentheses, if you do have to distribute, make sure you finish cleaning that up before you start moving things around with the addition property. I mean, you can start moving things across the equal sign now, but that'd be a little messy. You'd have to, kind of doubles your efforts if you haven't first combined all your like terms separately. Clean it up as much as possible before you start jumping that equal sign with your addition property. Does it matter if I move the negative 7x to the right or the negative 5x to the left? No. In fact, many people's instincts is to go ahead and move it to the right because that avoids negative numbers. I bring that up specifically because I'm going to tell you something different with inequalities. But for an equal sign, it doesn't really matter whether you're moving left or right with the variable, as long as then the constant goes on the other side. So you commit to which side you want each one on. Fractions or decimals, kill those first. Move either the LCD or decimals with the opposite of the place value, the power of 10. 10 to kill tenths, 100 to kill hundredths, etc. Remember, be fair to every term, whether it has a fraction or a decimal or not. I'm going to go ahead and do this one first just so I can then slide things up. So, if you're not there yet, that's fine. Don't look up until you're ready to check. No cheating. If this were not already locked up, sometimes it would just be 2x minus 6. Make sure you do lock it up. Because if anything's left over when you cancel out the denominator, it will have to be distributed. So any numerators that have binomials in them, lock them up. They go together. And anything that is left over behind to multiply times, it gets multiplied, distributed to the entire thing. Nothing left over here. It all canceled out. So nothing to distribute. I can go ahead and drop those parentheses now. But if you're consistent about that from the beginning, it will help avoid any careless mistakes when you do have something left over to distribute.
Oh, so you wouldn't multiply it as a minus 10. It would be just as minus 2.
Minus 2 where?
Right there. You would put it in front of after the minus sign.
Oh,
right.
That's what I do for consistency. My LCD is always going to be positive.
Yeah, it'll be the same.
Yeah. If you have a different way of organizing it, you're getting the right answer, that's fine. I always keep that LCD positive, and I just put it directly in front of the thing I'm multiplying. And I just make sure if this is subtraction, I keep that operation, and then it makes it negative.
together.
Yeah.
I got the same.
Yeah.
I don't know why I
Yeah.
got that.
Yeah. Yeah, there are other ways to approach it or to write, strategize on your paper. If you're getting to the right answer, that's great. But a lot of what I show you on model 1, because it's the way my mind works, and 2, because I try and model ways that make the most consistent sense to the most people. That doesn't mean you might have other ways to approach it. And if you're confused if your way is mathematically sound, then you want to ask about that, because you want to make sure it's actually something that's mathematically true, just a different approach. Any issues, problems? I'm going to slide down to this next fraction one. Remember, your LCD is always the largest or larger. Okay. If you go smaller than the largest one, then you're talking about a factor, and that's not going to kill all your fractions. You can't kill those denominators unless you're multiplying by at least the biggest one. If you multiply by something that's smaller, then when it cancels out, it's going to leave something behind on the bottom. Doesn't help you. So if 4 is not a multiple of 3 and 2, then you got to go higher than that. Well, it's a multiple of 2, but not 3. So 4 doesn't work, so you start counting by 4s. 4, no. 8, no. 12, yes.
So you multiply by 12?
Mm-hmm. There's 3 terms. All of them are fraction terms, so multiply them all by 12 over 1. But even if they were non-fraction terms, they still get multiplied by 12. Just like up here, you had 3 terms. One of them had the LCD, the 5. And the others you just multiplied by 5. Because if you're not fair at every term, that's our multiplication property of equality. It's an illegal move and unbalances your scale. Because it was as big or bigger than the biggest one. Everything that, and it was a multiple of everything there. That's what an LCD is. It's just a multiple, the least common multiple. It left ones on the bottom, but it did have left behind bits on top. That. I know we continue to work with fractions throughout the semester. Decimals we did at the beginning, and we kind of haven't really gone back to that. How many terms do you have in this last one? 2, exactly. This is like 3.4x, but instead of a simple x, it's a quantity x. Okay? So as long as that's locked up together, that's one term. You want to kill decimals and fractions before you unlock it. Because as soon as you unlock it, you distribute, you have 4 terms, and you have more decimals. Okay. Mathematically, that's not an incorrect approach. It's just not the most efficient approach. It's kind of asking for careless mistakes. What did I just say? That was, don't do that yet. All right, so the coefficients in front of our quantity x's are decimals. What's the biggest place value they go to? Tenths, right. And so we're going to multiply everything by 10. Yeah, the opposite of tenths, 10. And if one was tenths and one was hundredths, we'd have to multiply by the biggest one. Just like we want our denominator, our LCD, to be the biggest one or bigger, same with decimals. It should be the biggest one or bigger. Okay? So 2 tenths, we're multiplying both by 10. If they were both hundredths, we'd multiply them both by 100. But if one is tenths and one is hundredths, we'd multiply them both by 100. Right. So times 10. And because we leave this locked up, we are not multiplying times 10 inside here. That would be triple dipping. Times 10 times 10 times 10 to the same term. You'd be multiplying that term by 1,000 instead of 10. As long as it's locked up, you just have to multiply the outside thing. Using my addition property twice. Now, always, even though we start off with decimals, in general, leave your answer in fraction form. Just make sure it's in lowest terms. And if we're dealing with big numbers, your calculator can help you with that. 160, negative 160 divided by 74. Of course, it's going to return a decimal answer. And this is especially a decimal answer you should not use because you can see it's a repeating decimal. Okay? And you can write that, a repeating decimal is an exact answer. You can write it as negative 2.162 with the repeating bar over it. But we're not going to do that because you can't then go back and do the math with the repeating bar. Okay? You can't like plug that in and check your answer. Okay? So we always work with the rational form, the fraction form. Okay? So you can turn it into a fraction in lowest terms. So just entering this at all will help you to reduce it to lowest terms because you just do math, enter, enter, and you get it returned as a lowest term fraction. And as a reminder for checking your work, any of your work, you plug it in. Now you can manually plug it in and check it mentally. You can manually plug it in and do it paper and pencil. You can plug it into one side and push enter, then plug it into the other side and push enter, and if those answers match, you're good, balanced. Or probably the most straightforward, consistent thing to do is to use the test button. Okay? If you store this answer, you don't have to keep plugging it in and typing it in. So I would enter negative 80 over 37. It's already entered, so if I push store, it's already going to take that and store it. Okay? Or if I had erased it or had something else there, I would just type that in, negative 80 over 37, and I push the store button above the on key, store it in X, push enter, it says OK. It didn't actually, usually it'll change it to a decimal. It didn't in this case for some reason, probably because it's repeating. Okay, and then I go back and enter my original equation, exactly like I see it, if I'm going to use the test button, including the equal sign. 3.4 parenthesis 2x plus 5, close the parenthesis. Test, remember, is above the math key, so you use your second key to access it, and we're testing inequality. Now, by the end of the class, we're going to be working with inequalities, so note that you can check when we're changing to inequalities. If this is not an equal sign, it's an inequality. Look, 3, 4, 5, and 6 are a way to check your answer the exact same way. Store an answer, enter your inequality. Instead of just pushing enter to choose one, you would choose one of these others, 3 through 6. So you push enter to choose what you want. I want an equal sign, and then continue and entering negative 0.2 parenthesis 3x minus 5. 3x minus 5. Close the parenthesis, and I will get a true or a false. True. Okay. Okay with that? Okay. All right. So the solving equations, and even particularly solving linear equations, is foundational, a basis of everything moving forward in algebra. Okay? So you want a comfort level with any of these, from the simple to the most complex linear equations. You end up with one solution because linear is first degree, so you get one solution. And what does this solution mean if we were to graph the related two-variable equation?
That's where it intercepts the x-axis.
Right, it's our x-intercept. The related two-variable equation, if we took one of these equations, for example, and actually put it in standard form, so everything was on the left and there was a 0 on the right, then what that would mean is that 0 would actually stand for y. Y equals 0. And when y, that's the definition of an x-intercept. When y equals 0, x equals 7. So the related variable, then you could generate all these other ordered pairs, and you would get a line, and that line would cross the x-axis at 7. Okay. Now our answer, because these are, now if we had quadratics and cubics, we would solve them with either factoring or quadratically, what we just tested on, one of our other methods if it's not factorable. But for linear, we just use our general strategy. We get a single answer, one x-intercept for our line, and we write that answer in set notation using the braces, or the mustache brackets, the braces. Set notation is an unordered list, meaning you don't have to put what's in there in order. Now, if you had 2 or 3 or more solutions, you don't have to list them in order. It's nice to do it because it's easier for the brain to look at, but it's not required. Okay? And it doesn't include any in-between numbers. The answer is 7, and that's it. If you had 2 answers, if it was a quadratic, you had 3 and 7, then it would be 3, 7, and those are the answers, not everything in between 3 and 7. Just 3 and 7. Okay? So we're shifting now to inequalities, which includes a different understanding of what the answer means and a different way to write it. Now we're going to be using interval notation now. We already used that some back in Chapter 8 with looking at domain, okay, when you're writing a whole range of things. Okay? So we're going to use it again now to give solutions for inequalities. So we're going back to Chapter 2. We used to do this at the beginning of the semester, but I found it just too overwhelming with how much other information we start with at the beginning. And so it's kind of a nice, more gentle way to end the semester. So 2.9, and this is solving simple linear inequalities. Now when I say simple here, I'm not saying easy. Okay? There may be some easy ones, there may be more complex ones. That's not what I'm talking about. Simple linear inequality means you have one inequality symbol. Just like you have one equal sign, now you have one inequality symbol. Next week, 2.10, we're going to be working with what's called compound inequalities, which have 2 inequality symbols. Okay? So by simple, I mean a single inequality. These will all be linear. Okay? In college algebra, you learn how to do inequalities of nonlinear things, but ours are all linear. Okay. So, let's start with, here, 3x plus 5 is equal to 14. I'm going to leave space for 2 more columns here. There's your basic linear equality, linear equation. So you solve that using your general strategy. Simpler than the ones we just, less complex than the ones we just did. Kill fractions, decimals, and parentheses if you got them. And then start using your addition property. I'll do minus 5 on each side and divide each side by 3. This is linear, first degree. You get a single answer, a single solution. The related two-variable equation, which would be 3x minus 9 equals y, or equals 0, if y is 0, because if y is 0, there's no more y here, so when we solve for x, that would give us our x-intercept of the related two-variable equation. Now, if we were going to put this on a number line, which is not something I've asked you to do, but it's going to visually show the difference between this and the inequalities, is there anything, if I plug this back in, 3 times 3 is 9, plus 5 is 14. Yeah, that's true. This makes a true statement. This satisfies the equation. Is there any other value of x that will satisfy this equation? Anything else we could plug in that will multiply times 3 and add it to 5 will equal 14? No, that's it. Only one thing satisfies the equation. Now this is a single variable equation, not a two variable. Single variable we solve for one solution, two variable we graph on an xy graph. Well, this is a single one. single variable, so we're just using basically the x-axis rather than an x and a y-axis. Basically, it's a number line. Okay? Just the horizontal number line is like the x-axis. We're just dealing with one variable. Okay. So that's our basic number line. Our solution is 3 and nothing else. Okay. That's it. Okay. Single variable, we're not drawing a line or connecting dots, it's just that solution. 3 and only 3, nothing less than 3, nothing greater than 3. Okay. And we'll write in set notation the list of our solutions, which is a list of one solution. So this is the solution. Okay. And you have one. So you have one solution because it's linear, and it's written specifically in set notation. You don't have to. This is the correct way to write it too, but formally I've been asking you to use this notation. Okay. Now let's take that those same expressions, but instead of using an equal sign, let's use for one of them, let's use the less than symbol. And we'll also do the same expressions with the greater than or equal to symbol. Now you go about solving it in the exact same way. Okay? And there's one little exception. We're going to point that out in a minute when we do some more complex ones. But for these examples, you're just doing the exact same thing you do to solve your linear equation. Subtract 5 from both sides. Divide both sides by 3.
Wouldn't you do the greater than or equal to, since you're trying to find greater than 14? Is it like that? Is that what you're trying to do? Or?
No, this is the less than symbol. Yeah. And by using our general strategy, our addition and multiplication properties, to get x alone on one side and a number on the other, we're finding the values of x that will make this less than 14.
Okay.
Yeah. So any value of x that you get has to make 3x plus 5 be less than 14. Yeah. So is 3 a solution? If you plug 3 back in, will it make this true?
No.
No. Because 3 times 3 is 9, plus 5 is 14. And 14 is not less than 14. Well, what about the number 2? Yeah. 3 times 2 is 6, plus 5 is 11. That's less than 14. What about 0? Yeah. 3 times 0 is 0 plus 5. 5 is less than 14. What about 5? 3 times 5 is 15. Plus 5 is 20. That is not less than 14. All of our solutions must be less than 3. How many solutions do we have for this inequality?
Everything below 3.
Which is how many? Infinite. Right. With an equation, there is one solution that will satisfy. And so all we have to do is list it. It's not hard to list one number. We can't list all the infinite solutions because anything less than 3 is a solution. There's infinite possibilities. Infinite things it can be and infinite things it can't be. Okay? So in this case, here, 3 is the solution.